morning everyone. Let's proceed with the discussion on combinational circuits. Right. So yesterday we discussed how to construct any arbitrary Boolean function. Right. So if you have y equals f of a, b, c and so on. Right. Then you are going to assuming that this f is in a sum of products term, sum of min term 0, 1, 2 and so on, right. Then you basically convert this step 1, you convert this y to its complement function f bar of a, b, c and so on, and then implement the SOP expression in the NMOS stack, right. So you will get the pull down NMOS stack like this. It's called pull down network. The output y. For some specific combinations where the output goes to 0, y will be 0. Otherwise, y will be in its high impedance state in this network, right. Then you construct the dual of this, right. The dual is basically converting series to parallel and complementing the inputs, right. But of course, since these are all PMOS transistors, you don't have to connect the complement of the input to the transistor. Just connect the same A, B, C and you should be fine. Okay. So this is the pull up network to VDD, and basically you have the same inputs going to all of these. Okay, this is where we started with this discussion, and then we proceeded to sizing the transistors, because we have to now fix the widths of these transistors. Length is always fixed, right. So therefore I said that we considered the example of a NAND 2 gate, and if you had this implementation, which is very obvious, so I am not going through it in detail. A, B, A and B, output y, y equal to A, B whole bar. Then the size of this NMOS transistor was to be chosen so that the net pull down strength of that NMOS stack in the worst case is as much as it is for a reference inverter, right. And what is our reference inverter? It is basically this guy. VDD. So this is 1 and this is 2. And what does this 1 and 2 mean? This could be, for example, 4 lambda by 2 lambda. This could be 8 lambda by 2 lambda. Right? We are only talking about the width when we talk about 1 and 2. Right? Ideally, if area is a premium, I should keep my area as low as possible. So I would have liked to keep the sizes like this. 1, 1, even PMOS I would have liked to keep 1, but then we saw that because of mobility problems, you have to double it in order to get equal rise and fall delay, right. So that we made 2, 2. So I would have liked to make this 1, 1, 2, 2 for the NAND as well. But the problem is that if a unit transistor with 1 offers a resistance of R, then a transistor of width alpha will offer a resistance of R by alpha, right. So if this unit transistor now offers a resistance R and this is also R, the net pull down resistance is 2R, right. This is equal to 2R, but we want the net pull down resistance to be R, right. The reason is, see, now for NAND 3, when I go to NAND 3, I'll have a 3 stack. That will become 3R, 4R, and delay will keep going up. So somewhere we have to normalize this delay. The best thing to do is to, by definition, normalize it to the delay of the unit inverter, right? Given that we are going to increase the size of the transistor anyway, how much do I increase? I have to standardize that. That we are saying is make the resistance, worst case pull down resistance or pull up resistance, equal to that of a reference CMOS inverter, right? And therefore this has to become 2 and this also has to become 2, in which case the resistance will be R by 2, net resistance will become R, okay. So now we will proceed to something like the NOR gate, okay, or let's do a NAND 3 quickly. Y equal to A, B, C bar, right? So what do? I'm going to invert this function. I will get Y bar equals A, B, C, right? So I'm going to simply put 3 NMOS transistors in series, A, B and C. Right, this again is A, B and C. The dual is make all series, make it parallel, right, and connect the same inputs to those transistors. So now what should the size of the NMOS transistors be? 3R, right, because now there are 3 resistances. If I make this 3, 3 and 3, then each will give me a resistance of R by 3, R by 3 and R by 3, right. What should be the PMOS size? 2, because the worst case pull up path for the PMOS is only one PMOS pulling up. If all the PMOS transistors pull up together, it becomes a parallel combination and the resistance drops, right. So if the resistance drops, there is no problem, delay is getting better, right. So therefore I can keep the PMOS transistors at 2 always, irrespective of the number of inputs to the NAND gate, okay. Okay, so now let's look at the NOR gate, NOR 2. Y equals A plus B whole bar. So can you just draw the NMOS and PMOS stack first? Circuit. So what should be the NMOS transistor size now? 1, because I have a parallel stack now. Worst case is only one NMOS transistor turns on, it is 1, okay. So now if a unit NMOS transistor gave us a resistance of R, okay, this is size 1, okay. Remember the formula was R was 3 VDD by 4 ID SAT, okay. What would this transistor give us? PMOS transistor of same width, it will give you 2R. Why? Because the mobility difference is there, right. So if I look at this is NMOS, R PMOS, this is 3 VDD by 4 ID SAT P N. You take the ratio of the resistances, assuming that the widths are the same, it will eventually be the ratio of mobilities, assuming all the other technology parameters are symmetric. VTN equal to minus VTP, VD SAT equal to minus VD SAT P and all that. then all those terms will cancel. You are free to work out this expression for a PMOS transistor charging. So how did we evaluate the resistance for an NMOS transistor? We said that a capacitor was charged to VDD and this discharged to VDD by 2, right, and this went up instantaneously. What is the equivalent for the PMOS transistor? It is discharged initially and it has to charge to VDD by 2, right? So an identical scenario will occur there because the VDS of the PMOS will start from VDD and go exactly down to VDD by 2, right? So you can evaluate that just to tell you. So this would give me an equivalent resistance of R, that's what I'm saying. For the PMOS, this is NMOS. For the PMOS, it's basically, maybe I should write like this, right? And the capacitor is going from 0 to VDD by 2. Because that's the definition of delay for rise time, when the output goes from 0 to VDD by 2. Fall time is when the output falls from VDD to VDD by 2, right? And this has to drop instantaneously. So you can evaluate this expression. If the two technology parameters, VDSAT, VTN and all that are symmetric, then everything else will cancel out. You will be left with only the ratio of mobilities, right? And therefore, a PMOS transistor with unit width is going to be a resistance of 2R. Now, if I scale this up, the PMOS transistor by a factor of alpha, let's say this 1 became alpha, then what would my resistance become? That is the key. This is an equivalent resistance of 2R by alpha. Okay, so what I'm going to now do is I'm going to say that the width size of these PMOS transistors are all alpha. I want this resistance therefore is 2R by alpha, right? The top transistor offers another 2R by alpha, and therefore the net resistance is what? 4R by alpha, and I want this to be equal to R. The pull-up resistance should also be equal to R, because we have, like you can just say that even the pull-up resistance should be the same pull-up resistance as offered by a reference inverter that we have already sized twice, so it's the same thing. So if I say this is R, implies alpha equal to 4. So from the inverter, it's not surprising if you stack transistors, you need to add the, multiply the width by the stacking size, right? So unit inverter is 2, NOR 2 is 4, NOR 3 is 6, and so on. Okay? Any questions here? So let us look at maybe a slightly more involved example. Y equals, let me say, if I have A plus BC into D whole bar. So can you implement this CMOS logic first, then we will size it. So what are the sizes now for the, tell me for the NMOS. So first thing, what is the worst case pull down path? B, C, D. So therefore the sizes should be, yeah, 3, 3, 3, right? So 3, 3, 3, right? Now what should the size of A be if D is 3? Ah, correct. 3 by 2, it can't be less than 1, right? That's a golden rule because the inverter has size 1. You can't get less than that, right? So therefore, if this is alpha, let's assume this is alpha, then this resistance is R by alpha, this resistance is R by 3, and I want R by alpha plus R by 3 to be equal to R. Therefore, alpha will be equal to 3 by 2. Okay. Now, what about the option where this is made 4, 4? If both are 4, then what should D be? 2, correct? So this will be 2. Now if this is 2, then I can make A also 2. Which one will you choose? Yeah? First one, why? Lowest? Lowest width or lowest something else? Can you tell me what the summation of WIs is in both cases? This red one is how much? 12. Black one? 11 and a half. Correct? 9 plus 1.5, 11.5. 10, oh correct, sorry, 10.5. So which one will you choose? The black one, because that has lesser area, right? So in fact, this style of sizing where you size one gate, one transistor higher than the other deliberately is also allowed, but that is basically, it will come in when you're doing skewed sizing, okay? Essentially what's happening there is, we are preferring one input over the other input, okay? So I'll come to that at a later point, but for now, pick the one that has least area, okay? And no other configuration is going to be useful, right? And of course, the point is between B, C and D, if you cannot pick one input to be more critical than the other, then you have to keep all of them the same size. Otherwise, what happens is, depending on which input is switching, you might get a different delay, right? You don't want that, right? Or the load that input is offering to the previous gate will be very different if you size it as 442, right? But if there is no reason to pick that input and specifically sacrifice the delay on other inputs, then you don't adopt that in general, okay? In any case, the area is lesser in the equal assignment case, okay? So what about PMOS? What should D be? 2, right? There's only one transistor path there, no problem. Now A and B, it could go A and B or A and C, right? So B and C should be similar sizing, and therefore this has to be 4, 4 and 4. Okay.